In the earlier two parts of the normal distribution videos, we saw two examples. Well, this example is something which is different. Actually, we are going to make use of another function in this particular example. So the problem over here states that a fast food restaurant is there which sells perishable items A's and B's. And on a typical weekday, the demand of A's is seen to be normally distributed. Demand of B's is seen to be normally distributed, but you will find that the normal distributions in both the cases are different. And that's fine actually, because the items are different. That's why the parameters are going to be, where parameter values are going to be different. Okay. Now, our first question over here is how many A's must that particular restaurant stock to be 98% sure of not running out of stock on a specific typical weekday. Whatever the weekdays distribution we are having, our question is only pointed towards that. Okay. Now, similarly, the question is there of B and C is totally different. We'll solve this one by one. Hence, as you find over here with our first question, that how many A's must restaurant stock to be 98% sure of not running out of stock? First of all, let us consider what is distribution of A. Say let us XA be the variate which denotes demand of A pieces, which actually follows a normal distribution with mean 313 and variance 57 square. Fine. Now, let us draw the bell-shaped curve relevant to our numerical problem. As you will find that, well, this is our middle. Yeah. And in this case, what has been given is not the value. You see, we want 98% surety of not running out of stock. Actually, if we talk about 98% surety, you see, this is right side is the higher end of the demand, and left side is the lower end of the demand. Now, if we are going to make sure of 98% sure of not running out of stock, then obviously the demand is going to be at the higher end. Well, so I can say over here that, this whole area which we are actually considering, okay, this whole area, 98% in terms of probability is nothing but 0.98, fine, 0.98. And this area is 0.02. Okay. So over here, that's exactly reverse. What we see is we have probabilities and we want to find the value. Okay. See, in the earlier examples, if you remember, we had a scenario in which we actually wanted to find probability and had this value, or wanted to find this probability and had this value. See, for finding this probability, CDF function will be sufficient. For finding this probability, well, SF function will be sufficient. Now, the scenario is different. We have been given, you see, in this case, we already have been given the probabilities of these two, and we want to find this. Now, none of the functions like CDF and SF are going to be of use for us. Fine. For this scenario, the function which is going to be of use for us is PPF function. Let us see that PPF function. This is the PPF function. In this PPF function, we need to specify the probability which is at the left, that is 0.98. Now, what is Q over here? Quantile actually. Okay. So we are going to specify the which quantile we want to find. We want to find 98th quantile over here. That's why 0.98. And then mu value and sigma value as usual. And with this, we will be able to find the value over here. Let us execute this function in our Jupyter notebook. Over here, we have written this function. Let's execute this function. And hence we have this value. Well, this value is, well, 430.06. Let's round it up to 430.06. Well, this is the typical value which we actually have over here. Okay, and this is the value for 30.06. Okay, let me write down that value over here. 430.06. Let's talk about 430 only. So this is our answer. Okay, so what is the interpretation? That if the restaurant wants to be 98% confident of not running out of stock, then it has to stock 430 pieces of A's so that it won't run out of stock with probability 98%. Fine. Similarly, also is our second question over here. How many B's must the restaurant stock to be 90% sure of not running out of stock on that particular given day? Now, I make use of the same function over here. Only the thing is I require to change it to 0.9, 0.90, whatever. And B's parameters are 93 and 22 respectively. So I accordingly make a change over here, 93 and next being 22. And hence by executing this, we have the answer. So to interpret this answer, the restaurant has to stock 121 pieces of B's with which it will be 90% confident that it will not run out of stock for item B. Okay. Now, over to our last part of the question, which actually is asking us that if restaurant stocks, so if restaurant decides upon the policy of stocking 450 A's and 150 B's, what will be the probability of running out of stock either for A or for B or for both on that particular given day? Now, over here, it's not unusual or it's not wrong actually to assume that the two items are probabilistically independent. Okay, so that's why we are assuming over here that demands of A and demands of B are probabilistically independent. Fine. So as we consider, well, there are two variates, XA with demand of A and XB with demand of B. Well, what we are asked to find is probability that XA, well, XA exceeds the demand of 450. Why am I saying this? See, in spite of stocking 450 A's, if A is going to run out of stock, then definitely the demand of A is going to be bigger than 450, right? So A going out of stock is can be formulated as XA bigger than 450. In a similar way, B going out of stock can be formulated as XB bigger than 150 because we are going to stock 150 Bs. And the probability which has been asked is A or B or both. It is actually, see, both means intersection. And if it's inclusive of all, then it is nothing but union. Okay, union. We very well know from addition theorem one thing for sure, that if A union B is to be found out, then it will be probability of A plus probability of B minus probability of A intersection B. Now, very easily, let me tell you that this part of probability and this part of probability C, according to us, this is A and this is B. Well, we can easily find these two probabilities with the help of SF function, as we already have seen. Now, question is to find this intersection probability. How are we going to find that? Let's see that. So over here, if I want to write that I want intersection probability XA bigger than 450 intersection XB bigger than 150. Over here, as we have already assumed one thing definitely, that these are probabilistically independent. Well, that's why we can definitely write one thing by our statement of independence. We, as you may be already knowing, if you have forgotten, then let me also write it down over here. If A and B are independent events, okay, then probability A intersection B can be calculated as probability of A multiplied by probability of B. With this consideration of independence, this probability can be found as probability XA, well, bigger than 450 multiplied by, probability XB bigger than 150. So we will be able to find this probability with SF function. Well, this probability with SF function, once we find these two probabilities, we can multiply these two probabilities for finding the third term, and hence will be our computation done. These three statements are performing the same thing what I was telling you. So in this case, what we are doing is we are finding PA, then PB, and then we are subtracting the product from the addition. Let's do this in our Jupyter notebook. As you see that we execute this and we have got this required probability. So interpretation that either A or B or both may be running out of stock with probability of 0.012 if the restaurant stocks 450 A's and 150 B's. Hence, this concludes my 3-video series on videos of normal distribution. Well, this Jupyter notebook link on GitHub will be posted in the comment section or in the description section of the videos. For more videos from me, please subscribe to my channel and also press the bell icon. Thank you.